if f has a power series representation at a, f of x is equal to the sum from 0 to infinity Cn times x minus a to the n, then Cn is equal to the nth derivative of a divided by n factorial. So what this is saying is that if we have a power series in general form, the Taylor series is just like the power series, except it doesn't have this ambiguous Cn for the coefficient. It has a formula, that is this, that figures out what that coefficient is. And all that is done in the Taylor series that is different from the power series is that this Cn is replaced by this formula. So here's the Taylor series. Instead of having Cn, this is replaced in there. So instead of having a power series written out like this, C0 plus C1 times x minus a plus C2 x minus a squared, continuing on, here, when this power series, or this Taylor series I should say, goes out, it is f of a plus f prime a over 1 factorial times x minus a plus f double prime a divided by 2 factorial x minus a squared. All that's happening is that this formula is being filled in, and we are writing this series out like that. So to get an understanding of what all this coefficient stuff is about, it's easy just to have a look at where this comes from. So take a general power series, f of x is equal to the sum of 0 to infinity Cn x minus a to the n, and write it out. C0 plus C1 x minus a to the n, continuing on. And see what happens if we put f of a into this equation. So the whole point here why we're putting f of a in is because, great, we have this power series, but we need to figure out what these coefficients are. And one way to figure out what these coefficients are is to figure what they are one by one. So here's what we're doing. We put in f of a, then if x is equal to a, then all of these will be 0. This will be 0, this will be 0, this will be 0, this will be 0. And the only one that won't be 0 is this first coefficient right here. So at f of a, whatever that function value is, it's going to be equal to this coefficient. So that's how we figure out what that coefficient is. But what about the rest of the coefficients? Well, in order to find out what those are, we just take the derivative of this. Take the derivative of this will drop out, and we just bring down the powers. So we have C1 plus 2C2 x minus a, 3C3, 4C4, and all the powers are reduced by 1. And again, f prime of a. All of these will be 0, and the only one that will be left is the one that does not have an x in it, which is C1. So f prime of a, now I have C1. To the next one, take the derivative of this whole thing now. So now I'm to the second derivative. F double prime of x is equal to 2c2, and bring down the powers again. 3 times 2. Now I didn't multiply these together, and it will become obvious why in a moment. So here, bring this 2 down just like a regular derivative. Now it's to the first power. 3 times 2, now 4 times 3 times c4 squared. And continuing on. And again, put in a. This is 0, this is 0. What I'm left with is 2c2. And I can figure out what c2 is from there. F triple prime. So I'll be left with 3 times 2 times c3, and then this last term will become 4 times 3 times 2 times c4, x minus a. So now we should see a pattern developing. Now put in f triple prime of a. That will leave 3 times 2 times c3. And one more, f quadruple prime, I guess, of x. And this will leave 4 times 3 times 2 times c4, and then there would be other terms as well, but I don't need to bother with that kind of stuff. And then f of a, 4 times 3 times 2 times c4. So we can see this pattern developing. If we did this another time, it would be 5 times 4 times 3 times 2 times c5. So this pattern is developing. F of n of a is giving 2 times 3 times 4 n times cn. Whatever the coefficient number is, that is how many we're going to multiply. If we're to the fifth one, it's going to be 5 times 4 times 3 times 2 times 1, but we don't include 1. If it's 8, it's going to be 8 times 7 times 6 times 5 times 4 times 3 times 2. So what we can do is just simplify this formula to f, the nth derivative of a, is equal to n factorial cn. And what is done here is just dividing n factorial to the other side just to give cn. Cn is equal to f n derivative of a divided by n factorial. So that is where this replacement for the Taylor series comes from. It comes from the fact that if you put in a, it's going to make all of these other terms in the series 0, and it will leave just the coefficient that doesn't have an x there. And you keep taking the derivative, and it keeps leaving just one coefficient, one coefficient, one coefficient. And to simplify this, we write it like so. And we see this effect where it's 4 times 3 times 2, where it's because we keep decreasing the power every single time. So we started here up to a term that goes to the 4th power. So we take the derivative, the 4 comes down, and now the power is reduced to 3, and then we take the derivative again. So then the 3 comes down, then this is 2, and take the derivative again, now this is 2, take the derivative again, it's 1, but we don't really count that, and it's just left with c4. So we can see this pattern developing. And that is basically how the Taylor series works. The Maclaurin series sometimes is mentioned here as well. The Maclaurin series is just like the Taylor series, but this a is 0. That's it.